Hello everyone and welcome back to Operating System Lectures. On the series of concurrency and synchronization, here we are going to discuss the concept of semaphores. So let us begin. Talking about what are semaphores and what was the reason of developing semaphores, right? So first thing you need to know that the semaphores was actually developed by Distras. As a computer science students in the subject DA, that is design and analysis of algorithms, you have must have actually studied Distra's algorithm, right? So he was of a Dutch origin and he gave rise to the concept of semaphores, which are actually meant to implement mutual exclusion in concurrent processes, right? So we know the concept of critical section problem, that we have certain shared resources. What we have certain shared resources, and there are several processes in the system, right? There are several processes. What these processes are trying to do is to access these shared resources, right? But the problem is they may try to change the value of these shared resources, right? Or might be possible one process hold this particular resource and other process is waiting for them, right? So this is not desired, right? Because this can have discrepancies of value, as well as it can allow the issue of deadlock also, right? So this is not allowed. So in critical section problem, obviously we have multiple processes in the environment, and they are constantly, what they are doing, they are accessing shared resources, right? Which can give rise to race condition, right? We have already discussed race condition in the previous videos. Therefore, the processes have to access the shared resources in mutually exclusive manner. Now, one thing you need to understand, that over here we are studying operating system, and operating system is nothing but a software. And software is a collection of programs, right? The software is nothing but programs, and programs are written in a programming language, right? So in order to create an operating system which can work in multi-process environment, right, we need something programmatically to allow mutual exclusion. So what is semaphore? Semaphore is a programmatic way of achieving mutual exclusion in concurrent environment, right? So let us see what are semaphores. Semaphores over here is nothing but an integer type variable, right? So what are semaphores? Semaphores are nothing but variables, right? As in programming language, we can initialize, let us say example of C language. So we can initialize an integer type of variable as int x equal to, let's say, 1, right? We can initialize it like this. So what are semaphores? Semaphores are similar to variables, right? So what are the uses of semaphores if it is a variable, right? So you can see this animation over here. Of course, most important use of semaphore is mutex, that is providing mutual exclusion, right? But semaphore can also act as a notifier. You can understand the working of semaphore as a notifier with a simple example. You have seen a linear search, right? You have seen linear search. Let us say there are several elements, and let's say you are searching for x over here, right? So what do? You'd go over here and find if it is equal to x or not. Then you go over here, the value over here is equal to x or not, then here and then here. Now, as soon as you find x, what do? You change the value of flag equals to 1. And before that, you have initialized flag as 0. Right? So, by changing the value of flag as 1, you are notifying in your program that yes, we found the value. Right? So, similarly, we can use the variable semaphore as an notifier. Next thing is as a counter. Yes, you can use semaphore as a counters also. There are two types of semaphores which we are going to study in the upcoming slides in this video only. That they can also act as counters. and as a counter they keep track of processes and resources, and that will be clear in the upcoming slides. Now, as we have said that what is semaphore? Semaphore is an integer, right? So obviously as an integer, what you can do on it, right? So you can understand that you can do only three things on a semaphore. The first thing is that you can initialize the semaphore, right? As you can see over here, it is a C programming language syntax which says int s is equals to 1. So here s is a semaphore and we have initialized its value to 1, right? The first thing that you can do on a semaphore is initialize its value, right? After initialization, you can perform only two operations on a semaphore, right? What are those two operations? The two operations are known as wait and signal, right? These two operations are known as wait and signal operation, right? There is a difference between a normal variable and a semaphore. We have said that semaphore is nothing but a variable, right? But semaphore is not a simple variable. It is to be understand that there are only these two operations which you can see on your screen right now, that is the wait and the signal operation. We can do only these two operations on semaphores, right? But if we talk about normal variables, we can do addition, we can do subtraction, we can do division, we can do multiplication, we can do a lot of things on other normal variables. But on semaphores we can have only two operations, right? And these two operations programmatically are written in a method or a function, which is wait function and signal function, right? So in order to understand wait, it is said that it is decrement operation, right? Understanding about wait, wait is decrement operation. That means you decrease the value in wait. And talking about signal, it is the increment operation. That is, we increment the value in signal operation, right? Now, talking about the wait operation. Wait operation says, so in the wait method, after decreasing the counter by 1, if the counter value becomes negative, then add the caller to the waiting list and it blocks itself, right? And in the signal operation, after increasing the counter by 1, if the value is not positive, then remove the process from the waiting list and resume the execution of the process and return. Now I can understand that this particular explanation would be a little bit overwhelming, but you can pause and write down these points because these are very important as far as the written examinations are concerned. But in order to understand, let us move to the next slide. Now before getting into the proper explanation of what I said before, is you need to understand that there are two types of semaphores, right? The counting semaphore and the binary semaphore, right? Now here you can understand that binary means 2. So in binary semaphore, we can initialize the value of semaphore with only 2 digits, that is 0 and 1. Whereas in counting semaphores, we can initialize it to any sort of number, right? Any sort of number, right? You can see that in the example I have said that x is equals to 9, right? So binary 0 and 1, in counting it can be any number, right? Now in counting semaphore, what we do is, if we initialize the value, let's say to 9, it says that at a given point of time, only 9 processes are allowed to access a given resource, right? As soon as the number of processes get greater than 10, right, the processes will get blocked in the waiting queue, right? So counting semaphore allows multiple processes to access a resource. How many processes? The initialized value. Here if I say that s is equals to 9, it means that we can perform 9 successful wait operation. right? 9, successful wait operation. Let us understand the working of counting semaphore with an example. Let's say that the value of semaphore is equals to 4, right? It means that there is a resource which have 4 units, right? You can, let's say like this. There is a resource which have 4 units, right? So a process P1 comes and says that it want to access the resource. It will be performing wait operation on it, which is a decrement operation, letting the value of S to be 3. Okay, it is a positive value. Process P1 can access this resource. Then P2 comes, decrement it to 2. P2 is allowed to access. Then P3 comes, decrement the value to 1, positive value, P3 is allowed, right? P4 comes, decrement the value to 0, positive value, P4 is allowed. Now, there is another process P5 who comes and again decrement the value of S by 1, letting the value to be -1. Now, as soon as the value becomes -1, right, by applying wait method, it says that now all the units of this resource has been utilized. So, process P5 has to go into the waiting queue and have to wait until and unless any of these 2, 3, 4 processes actually leave any unit of this resource. So, that is the working of counting semaphore. Whereas you can understand the value of binary semaphore is through this. Let the value of S be 1. Wait operation comes, a process comes, let's say a process comes, right? It decrements its value to 0, right? It decrements the value it to 0, right? And this is allowed to access any resource. Now another process P2 comes and try to decrement this value, this becomes -1. That means the value of binary semaphore will be working only with 2 processes, right? So that is the small way of understanding the working of semaphores. Now let us understand it in a deeper manner. So first of all, understand these arrows. Here this red arrow signifies that now a process in its critical section. A normal black arrow signifies the normal execution. Critical section is where there are shared resources, right? So in critical section, there are shared resources. And the dashed line signifies that right now the process is blocked, right? So there are 2 processes, process A and process B. So we have 2 processes. Here we will be making use of binary semaphore, right? So this is the value of semaphore. Semaphore is initialized as 1. Right? Now suppose process A arrives, right? And it is executing, right? Process A is also executing and process B is also executing, right? During this execution, process A reached its entry section, right? In entry section, what we have wait operation, right? So it is performing wait operation on lock, right? Here lock is the name of semaphore, right? It is nothing but the name of the semaphore, as we can give any name to any variable. So here semaphore, the name of semaphore variable is lock, right? So it is performing decrement operation on lock. So by performing decrement operation, the value of semaphore lock becomes 0, right? And you can see that this value is positive. Because this value is positive and it is performed by process A gets into its critical section, right? Meanwhile, process B is executing, right? And you can see that here process A is in its critical section. So if one process is in its critical section, semaphore must not allow any other process, right? So what happened, process B also wants to get into the critical section, and the situation is one process is already there, A is already there. So let us see, process B wants to enter the critical section. So in its entry section, it is seeking permission, right? So for this permission, what this process is doing, it is performing wait, that means the decrement operation on lock, right? Here you can see now the value of lock is equals to 0. So now this was performed by process A, and now process B performed another decrement operation on your process, on your lock variable, and now this value becomes negative. So you can see that the value becomes negative by which process? Process B. So it says that process B, one process is already, see the value, it is -1. -1 over here indicates that there is one process in the critical section, right? So what you have to do, you have to wait in the waiting queue. Right now you are not allowed to get into the critical section, so kindly go into the waiting queue and wait. So B process is in the waiting queue, right? So it is now been blocked. You can see the dotted lines over here. Meanwhile, what happens? Process A completes its critical section. Now what process A will do, it will free the variable lock so that B can get into the critical section. So for freeing that particular lock, what it will be doing? It will be operating signal operation on lock, right? So by performing signal operation, it increments its value by 1, and now it becomes positive by 1, which makes B out of the queue, right? And as it becomes positive, B get out of the queue and gets into its critical section, and process A resume its normal execution. And now when process B completes its critical section, right, it will free the lock. Why? So that any other process can get into its critical section. So in order to free that particular lock, it will perform signal operation again, and by performing signal operation we will resume the initial value, that is 1, which was initialized originally. So that is the process of providing mutual exclusion with the help of semaphores. I hope that this process is now pretty much clear, right? This makes the process block, and this makes the process resume, right? That you need to understand. Now I think up till now the working and the importance of semaphore will be pretty much clear to you all, but there are some certain disadvantages with semaphore also, which is very important. The incorrect use of wait and signal operation can give rise to deadlock and starvation also. Let us suppose that the order of wait and signal should always be this only. First, there should be wait operation, and then second, there should be signal operation. Remember, wait is in the entry section and signal is in the exit section. Suppose that we perform the opposite ordering. Suppose the value of semaphore is 1, right? And instead of wait operation, we perform signal operation on it, right? Suppose one process comes and it performs signal on it. So the value becomes 2, right? And if another process comes and then it performs wait, it says that the value becomes 1. That means process P2 is allowed in the critical section, right? Another process comes and perform wait operation, it becomes 0. Another positive value, then P3 is also allowed to get into the critical section. So the ordering is very, very important. Wait should come first and then signal should come. If the ordering becomes reverse, it will be getting lead to deadlock, it will be getting lead to violation of mutual exclusion. Two processes will be in the critical section. Similarly, if we perform wait operation, suppose we forgot to apply signal, right, and we perform two wait operations, right? So if S is equals to 1, we perform wait operation, a process comes and perform wait, the value becomes 0, another process will come, right? The process P1 will get into the critical section, process P2 comes, right, and it also performs the wait operation, right? It also performs the wait operation, then the value becomes -1. And after leaving the critical section, instead of performing signal operation, it performs again wait operation. The value becomes -2, right? So this will not allow process P2 to get into the critical section. It will not allow it. That is why it will be leading to deadlock. And also omitting any of the operation, that is the wait and signal, can also lead to starvation. The process will not proceed further because they will be in the waiting queue for indefinite time. So you need to understand that always wait operation comes first and then it is the signal operation, right? So that is why I said that it is in the entry section and it is in the exit section. So you need to understand that. Right, so that was all for semaphore. I hope that you understand the concept of semaphore pretty well. And for more such videos on operating system, stay tuned to my channel. Thank you.